Wow, I don't know what to say after that. Thank you, David. I want to start off by just mentioning Jim Simons. He was a mathematician and chair of math at Stony Brook University on Long Island in New York. I went to Stony Brook, and I actually, took the math courses there as a computer scientist. And it's just a really interesting coincidence that basically the Jim Simons Foundation has funded our AIRS project, which Claudia mentioned earlier. And this is the Jim Simons lecture. So it's a real true honor. And in that light, I will be talking about math and modeling and physics and how important it is to get those things right. Foundational principles, first principles, so that we deliver better care. So let's move on. These are my conflicts. And I'll start off by, let's just talk about measuring small nodules changing over time. Now, these are all stable nodules. They have pretty good segmentations, although they're a little hard to see, sorry for that. And it can be quite challenging to determine whether a 3, 4, or 5 millimeter lung nodule is changing enough to warrant thinking it's a malignant process, right? And as David was saying, and also Claudia this morning was saying, if you really, really want to give high performance, reliable AI solutions, you have to take some ownership of the pipeline, the whole pipeline, the acquisition system, the protocol. There is no going back. There's no AI that can take an image that's you've lost half the resolution and bring it back. It's not going to happen. There are some ways you can recover some things, but for the most part, once it's lost, it's pretty much lost. So I'd like to start off with one of the more important areas that I think as a community we need to focus on, and that is on setting recommendations and guidelines. There are major organizations setting recommendations and guidelines, and they're shaping the quality of data being collected around the world. Every time a new clinical site comes online, they do a Google search. What do they find? They find recommendations from LungRads, from British Thoracic Society, from AAPM, from several others, and they follow them. So it's extremely important that those guidelines give the right information on what to do. I'm just going to summarize probably the number one recommendation right now in the United States is LungRads, right? And basically it primarily relies on bidimensional measurements, but it's now moved into some volumetric use for assessing the size of nodules. And there's some major thresholds in it, 4, 6, 8, 10, 15. And they give the volumetric equivalent for a sphere. We'll come back to that in a little bit. But 4 millimeters, I don't know if you understand how incredibly hard it is to measure change of a 4 millimeter lung nodule. I mean, I think I might do better with a coin flip, honestly. It is way beyond what most people are doing with their scanners and their protocols. And I'll show you why. But the main thing I want you to focus on is the definition of change. So most of the world is doing bidimensional measurements and measuring change with 1.5 millimeters as the cutoff. You can see Fleischner is 2. And we, with Jim and with David and with many others in this room, we developed guidelines inside of the small lung nodule profile that basically give a table, a size-dependent table, and basically says, well, if you're at a certain size, here's how much change you can expect, and gives the math, the metrology math for figuring out when is the change enough to overcome the errors in the scanners and in the software. So let's take a closer look now at this 1.5 millimeter requirement. Fortunately, as part of Kiba, for many years, actually years ago, we created a CTLX-1S phantom. That means it's for evaluating software. And what we did was we took the standard CTLX phantom, which is these 3 modules you can see here. I don't know if I can do this. Yeah, okay. You can see those 3 modules right there. Those measure fundamental properties. That builds a mathematical model of the acquisition system from isocenter out to periphery, and that model is extremely useful for understanding the quality of the scan. But we added 2 cylinders to it with 80 small ellipsoids, acrylic ellipsoids. And you can see the sizes. It goes from largest diameter of 6 millimeters to 7 to 8 to 9 to 10, and there's 16 of them. So you get 80 measurements in one scan. Great data set. It was scanned all over the world. It was scanned on neotome alpha scanners. It's been scanned on 16 slice scanners. It's been scanned on everything, just real large numbers of scanners. So it's a wonderful resource. Somebody in the room scanned it, and you can see on the bottom, we want to thank Mario Silva, and he went and measured all of those spheres. And what we thought was, okay, we're going to measure 1.5 millimeter changes. So you can see here we go in the top row, we go from 6 millimeter longest diameter to 8 millimeters. You might say that's a 2 millimeter change, right? But if you use bidimensional measurements and you work out the trivial math here, it's really 1.6 millimeter change. And still, that's above 1.5. And if it were to do that, it would have a volume doubling time of 293 days. So when we looked at Mario's measurements, which were manual, how many of them exceeded 1.5 millimeters from going from 6 to 8? It turned out to be 58%. And for the next size up, for 7, it turned out to be 70, and for the one up higher, it turned out to be 64. This is almost perfect data. This is an ellipse, acrylic ellipse. It's not a complex lung nodule in a real biological system. So we're talking about a system that's being used around the world, that fundamental property of measuring growth, which will basically increase the aggressiveness you have to handle a nodule, is not detecting a good percentage, 30, 40% of simple objects, and it goes down to 4 millimeters. 4 millimeters grow, 4 millimeter nodules growing. Those numbers are going to be much worse than anything you see here. We didn't have the data in this data set. But I think you get my point. Very concerning that the method that's being used is not able to measure, in about 40% of these simple cases, what it's supposed to be measuring. Now, you could argue, well, that's factored in and blah, blah, all kinds of other things. But in the end, the methods should be consistent. And it can be much worse than what you're seeing here, as I mentioned. Of course, if you miss growth, especially aggressive growth, there's chances for treatment delays, detection delays, and potentially cancer upstaging. This is not a small thing. We only measured the right side of this, right? The false negatives, those 2 false negatives on the right side column. So how could this be? How did it happen? What's going wrong? So let's get down to the fundamentals. First of all, bidimensional measurement works poorly on ellipsoids. There's no guarantee that your nodule is going to be a sphere. And the main assumption right now with our guidelines is that everything's a sphere, okay? Or all the volumes being given, 113 millimeters corresponds to a 6 millimeter diameter sphere. So what happens if you take 16 of those 6 millimeter ellipsoids and you measure it with diameter or you measure it with volume? Well, your cross sections are going to be completely different because they're at different orientations. And the coefficient of variation with a diameter is 13%, and the coefficient of variation for a volume is 3%. That's a 400% difference. So, again, when we're measuring small nodules, we not just have to worry about spherical ones, we have to worry about complex shapes, complex aspect, well, different aspect ratios. And this data, and it's a simple model here, but this shows the power of volume. Volume looks at the change across all 3 dimensions, whereas a diameter can only look at a single axial plane. A second reason, it's that whenever you look at these types of problems, this falls into the class of metrology. And what you'll get to is what's the bias and precision of your measurement. And in this case, it's the measurement pipeline. It's the scanner and the software. And so what do we have? Every time you measure by eye or with AI or any method, you measure an ellipsoid or a sphere, you're going to get a bias inward, smaller. That's because the convolution of what's called the point spread function, or the resolution of the scanner, is going to, with a convex object, which is what it is going to give you a smaller number. So your eye is going to tell you that the boundary is at that light green location. Whoops, wrong one. Your eye is going to tell you you're out here when, you're in this light green, when it's really out in this dark green. That is a predictable, it's a predictable relationship. And you can see an example I included down in the bottom there. It turns out the computer vision literature is pretty well, has pretty well explored the biases associated with edge localization and advanced edge detectors like canny edge detectors and others. So this fellow, Paulo Mendonça, who used to work in my AI group back at GE, published a paper in 2004, and he gives the equations, and then Banish went and showed what happens if you have a cylinder or a sphere. We use those equations in the Kiba profile to come up with the methods for establishing how much change is enough. And this is really important. You need to understand biases, you need to understand precision. On the right, any measurement system is going to have its set of biases and precisions. If you repeatedly take measurements, you're going to get a distribution. And you need to factor in those biases and precision, that precision when you set your recommendations. A third thing, which is quite obvious, and everybody admits it, but we're using a constant threshold for different size lung nodules. So this is a zero change data set from Mount Sinai. And the red curves are a model based on that math that I showed you before, okay, that bound the model for 0.625 millimeter slice thickness. But all of these green dots should be on a horizontal 0 line. They shouldn't be changing at all. But as you get down to 6, 5, 4, you can see the error blows up. Well, imagine now, you're going to let a recommendation tell you that the change of 1.5 millimeters, which here it's a volumetric thing, so I just put a dashed red line. You're going to try and say anything above that line is real change and anything below it is stable. No matter where you place the line, it's not going to be a good fit. It's a terrible fit. So what we're after is something that really captures the processes and the physics associated with basically how images form in the CT scanner. And a varying limit, like you see here, is what we use in KIBA, small lung nodule profile. And recommendations, I know it's more complicated, but recommendations need to start doing this to really guide people when change is really happening. You can't use 1.5 for a 14 millimeter lung nodule and expect to get growth when it's just above a rapid doubling time. So as I was saying before, recommendations must be developed on fundamentals, the math, the physics, the computer vision, the signal processing. And what do you need to do that with? Well, you need fundamental properties to work with. The equations that I showed you before are based on curvature and resolution. And once you have really good measures of resolution, curvature, and other things, you can look at the bedrock of imaging, which is these fundamental properties and trade-offs, like you see on the right. On the right, you can see that resolution and noise are interrelated, are traded off. So somebody was talking about applying a soft kernel to an image. You're giving up resolution and you're lowering noise. That's what that graph says. So you need to really understand this to set these guidelines and recommendations. A fun little experiment I did to just give you an example. This is a paper that said how much does noise go up as slice thickness goes down. And they went and did the scanning and they did the measurements and they published the paper. And so I plotted the blue curve. And with a very simple model of how noise and resolution vary, I took one of the measurements, which is circled in green, and I predicted what the others would be using, again, a mathematical model. And it came out actually better than I thought it would. The red, which is predicted, is almost completely overlapping the blue. And that's going to be true for all of your scanners. And I'd be shocked, actually, if you got something much different than this. Obviously, there might be some corner cases where some things get weird, especially if you use weird kernels. But anyway, so this is the power, again, of mathematics and modeling. And as David was saying at the start, if you're not constraining your data with fundamental physics and math, your AI is not going to perform. Your AI could actually do anything. So it'll be trained, but if it's not taking into account that. So here's another example. We developed a method. If you put 3 rolls of Scotch tape on your scanner, we would analyze it, build a mathematical model of your acquisition system, and then run a huge simulation and predict what the performance of different, basically the bias and precision of measuring spheres in your scanner was. This is a $1.50 Phantom. It produces better resolution measurements than I've been able to find in other Phantoms. We took that and we incorporated, we made a nice version of it for hospitals. And you can see that the prediction versus observed for the mean and the coefficient of variation, which is on the bottom, were quite good. It's actually, I've said it before, it's better than any other system that I know of in predicting the performance of volume measurement just with a simple calibration reference object. So we designed this new CTLX-1 Phantom a long time ago with RSNA Kiba. There's over 150 of them distributed around the world now. There's multiple models. You scan it within 5 minutes, you get a report, and it tells you, are you in a good place for measuring small nodules? It's very simple. It's meant for technologists and medical physicists, and it makes the process of understanding your quality of your system really, as easy as we can make it. It's based on three-dimensional resolution, which we use a Gaussian point spread function. We measure the resolution aspect, the linearity biases associated, basically linearity, image noise, kernel edge enhancement, and 3D spatial resolution. Did you see Claudia's slide this morning where she showed a 44% change in a 1.6 centimeter sphere sitting on the chest of a patient undergoing chemotherapy? We measure it here, and rather than say, don't buy that scanner or don't do this, which I don't ever want to do, we say, if it can't pass this test, we got a problem. And so where we could go, and I've shown this chart before, but imagine you really understood the precision of your measurements at your institution, and you had a 6 millimeter nodule, and you wanted to know, how much time should I wait before I scan again? Well, if you know the fundamentals, you can draw a line anywhere you want on this chart and see how much overlap there is and how much confidence do you want to have. Do you want to have 67% confidence, which is shown here with these green and red bands, or do you want to have a 95% confidence or more? So you can see here, even at a 90 days later with this level of precision, you're going to have a good amount of overlap between something that's 180-day doubling time and a stable volume, which is infinite doubling time. You can take these models and you can help educate people, which we did, and you can generate a model of what a good, ideal scanner from 2030. Remember, Claudia showed us a chart with a 2034 prediction. It wasn't a prediction; it was an extrapolation. But the same concept applies. What we did was we took two models, a canny edge detector and a thresholding, and we generated images of a scanner from the future that had 0.1 millimeter resolution. The ellipsoid has a 1 millimeter sphere through it. And we said, what would that look like? That looks pretty good. That's good. At the time I generated this, what was the best model that we got from anywhere in the world? It's the one to the right. The cylinder is starting to fall apart. The average small lung nodule passing grade, if we averaged all of those from around the world, it's what you see there. Now we're starting to talk about going from a nice ellipsoid to something that looks like a misshapen potato, or maybe an okay potato. But then you go to the absolute limit of the KIBA, or the small lung nodule profile requirements, and you get what you see there. And again, you're looking at two segmentation methods. Again, if you're using thresholding, it's the wireframe, and if you're using a canny edge detector, a three-dimensional canny edge detector, you see that surface below it. And there's a lot going on here, because the difference between those two surfaces grows. As you see that? It's very close with a really high-quality scan on the left, and on the right, they start drifting away. So what's that telling us? One of those models has more of a bias than the other, okay? So there's a lot in that image. It turns out that once you start doing all this and a pandemic shows up, you can turn around very quickly and tell the world, which we did with many people in this room, what's the best kernel to use to quickly get a handle on COVID-19. And we work with both institutions from around the world and the manufacturers of these scanners themselves. We verified, and we said these kernels, if you stick to these kernels, we can be more confident that you're going to get a better image for quantitative imaging. For at least we found it for small lung nodules. We published a paper showing for COVID-19. This is exciting to me because what this says is to the scanner manufacturers, basically these kernels matter. Okay, the world is relying on these kernels staying stable. You might upgrade your scanner, you might get a new scanner, but please don't really mess with these kernels if you can. And we'll measure it. We're measuring it every day, so we'll know. We have a new Phantom out now, which is the widest in the world, I believe. This is 3D printed, that white region outside, and it's concentric rings of PLA plastic that lets you approximate different size masses in the Phantom. I'm sorry, in the scanner, and this Phantom does everything that I said to you before, but now you can look at trade-offs between radiation dose and image quality. So in summary on these Phantoms, you can eliminate low-quality scans, you can assist with when scanners and protocols change, you can validate them, you can help establish new, let's say, better nodule measurement guidelines. And in the future, I showed you before, we should be able to set better follow-up times that are based on precision methods, not simple constants. Now, the whole talk is about how CT and AI, CT image quality and AI are related. So we had the pleasure of working with IASLC, building something called I-ELCAP, the Early Lung Imaging Confederation. And during that time, we did some experiments with the 700 scans that were distributed around the world. Seven sites around the world had 2 time point 100 case scans. And what you see here is we looked at if we wanted to separate the cancers from the controls, we basically said, how well does diameter, just a single diameter work, sensitivity and specificity for those 2 time points? And it turned out that you get the curves, whoops, I keep doing that. You get the curves up here. Not that great. Now, volume doesn't do much better, okay? Volumetric performance. But if you focus on the high quality data in that I-ELCAP data set from around the world, the difference was quite dramatic. And what this shows is that just some preliminary evidence that if you take care and put some quality constraints before your AI, you can dramatically improve, and I'll show you some more examples, but you can improve the quality of the measurements and the performance. So I'll move on and show you another example. I-ELCAP, who hopefully is in the audience online, I-ELCAP recognized all this and said to us, hey, let's take your Phantoms and let's look at the GE Revolution Apex, and let's figure out whether we can get a better protocol for the GE Revolution Apex. This is what scanner manufacturers should do. And so we spent a very long time scanning the Phantoms, I think over 100 times. And we also brought in Mevis. I think Mevis is here. And they joined in on the study by giving measurements on these Phantoms. And the bottom line is, after we looked at it all, after we applied what we know about signal processing, Nyquist basically theorem, and many other fundamental properties, we picked a protocol, and you can see that the bias and the precision improved by about 50%. Now, I went back to the GE team and I said, name me any other thing you could do with your scanner to get a 50% improvement in your measurement bias and precision. And literally within a short period of time and very low cost. And of course you can't. These systems were not designed for nodule measurement specifically, but once you optimize them with calibration and fundamentals, you can do great things to improve. And I don't think you could get there faster any other way, honestly. Mevis went and ran against this same data. We just gave them the data set. They took the measurements, and they got a 30%. It was not the same as this, but 30% improvement in bias and precision. So again, another data point. If you care about quality, if you focus on fundamentals, you can greatly improve volumetric, in this case, performance, and AI performance. So now I'd like to switch gears to AIRS. This is the Simons Foundation funded project that Claudia mentioned earlier for automated image reading system. The idea here is that we want to have a radiologist read a baseline scan and then on the next scan say whether any of the nodules have changed significantly, clinically significant. This is the website we're going to be posting the publications and the source code for the tools that we're about to release. The approach that we decided to do was to break down the problem into the familiar ones. We would do, participant selection, make sure we're not taking in surgery cases where everything is completely, different from others. We do our quality control based on fundamentals, segment lungs and lobes, nodule detection, nodule segmentation, nodule matching, and change assessment. Every step of the way, we compute confidence. And if our confidence gets too low, we say the radiologist has to look at this. I'm not aware of any product in the medical nodule space that computes confidence of their calculations and tells the radiologist. Secondly, if the confidence gets low and we tell the radiologist you need to look at this, we give the reason why in English, in radiology speak, if you will. And this approach has to be extremely high performance, right? You can't have a growing nodule pass through here and us telling the radiologist, you know what, don't take a look at this. Because if you did, you could really hurt somebody, right? So to give you an example of one of our components and the performance needed, well, let's look at lung nodule matching. We have a paper prepared on this one. And here's some examples of solid and non-solid nodules. You saw them before. We are getting right now in the I-ELCAP data on many hundred, basically it's about 400 opportunities, nodule matching opportunities. We're getting 99.5% performance. Is that good enough? Maybe, but we're gonna keep at it, and we're gonna be, I think, north of that. And this is on highly heterogeneous. This is data from all over the world, low dose, and now we had the luxury, if you will, to say, okay, some of these are going to be low confidence. But that's what I think anybody would do. That's what a human would do. If they had low confidence in looking at a case, they would tell you and say, I've never seen this before, so I really don't know. And that's what an AI should do. So here's the result, and I want you to focus on the end. So there's a percent matched correctly on 64 slice scanners, and there's a percent matched correctly on 16 slice or lower. And you can see we're way up there at 99 to 100% correctly matched. You can't mix up your nodules, right? But the confidence levels, the percent confidence of cases is like under 1%, okay, for the 64 slice. But what happened on the less than 16 slice scanners? We got like 6% of cases fell into the low confidence category. Why? Because people were coughing, because the scan times were longer, other things. But you can see the difference in quality, what the difference in quality can mean in terms of, we got the performance we needed, but the number of cases where the radiologist has to step in and do more work is higher with low quality data. So lastly, I've shown this before. If every year you come back and you know where a serious issue is in a scan, why can't we have an AI help the scanner do the best acquisition at that location, a targeted acquisition? So you could take an object, which is a 3D printed object. You see on the left, that's an ellipsoid with cones sticking out of it. That's what it looks like with basically probably what everybody's doing around the world now, 1 millimeter slice thickness. And if the AI came in and said, you know what, let's take the capabilities of this scanner and let's get an acquisition that's much better. Now all of a sudden you get the image on the right. And of course you could measure those spiculations or other things much, much better. In fact, the improvements can be, 600%, 1,000%. I mean, we did a bunch of testing on this, and there's no question that there's tremendous opportunity to improve the quality of the scans if you know where to look and where to target so if an AI comes in, finds something suspicious, now you target that area and you get much, much better results. And here's just some examples of what you can see on the right that is almost invisible on the left with this kind of an approach. Again, vessels that are there on the right, but almost impossible to see on the left. And then finally, I just want to say to you, we've also worked on phantoms that you can embed on your table. You can just put it on the table. This is a phantom. It's a prototype phantom we designed to do the same things that I showed you before, but it's 11 millimeters thick, and it sits on the table of the phantom. I'm sorry, on the table of the scanner. And we can detect the elements inside of it, and we can measure the 3D resolution. And in fact, we can, in one day, I hope, we can put in your DICOM header the fundamental properties of that acquisition system, a mathematical model of the system for every slice. And that's what this system should be able to do. Now, an AI who takes that in should be able to do a lot better optimizing their segmentations, their methods, basically throwing out data that they can't handle. It really is going to greatly improve our ability to do quality control on a not just a patient-by-patient basis, on a slice-by-slice basis. And so that's really where the future is. So in summary, look, AI for lung screening holds great promise, but we have still a lot of work to do to make AI tools more resilient. There's major guidelines out there. I ask that we focus as a community to help those guidelines build in more math, more models, more methods to ensure that the quality of the data that comes out of them is consistent and high quality. Controlling quality based on fundamentals is just the way, I don't know how to say it any stronger, the way to go. Improving quality, as David was saying, those images that I showed you before, they're so radically different than a CT image that you're collecting today that most AI systems won't be able to handle them. They're going to perform much worse, unfortunately. Finally, future integration of real-time AI and calibration, like I showed you, can greatly improve our ability to measure small features and nodules very precisely. So I want to thank you, and I'll let David say what's next.